Designed to probe the fundamental building blocks of the universe, the Large Hadron Collider at CERN routinely generates data that pushes the boundaries of known physics. Yet, the very nature of its complexity has also made it a magnet for fear-mongering. When the LHC first became operational, many were petrified with fear that it would end the world as we know it, and many, to this day, believe that it did, and we're living in a parallel universe now. In any case, fresh rumors have begun circulating online that CERN has picked up a pulse from beyond the observable universe. So, what really happened? Scientific anomalies at the LHC. The European Organization for Nuclear Research, widely known by its French acronym CERN or Conseil Européen pour la Recherche Nucléaire, is at the forefront of particle physics research. Founded in 1954 and located near Geneva on the Franco-Swiss border, CERN operates the largest and most powerful particle accelerator in the world, the Large Hadron Collider or LHC. Housed in a 27-kilometer circular tunnel about 100 meters underground, the LHC became operational in 2008 and was responsible for one of the greatest scientific breakthroughs of the 21st century, the discovery of the Higgs boson in 2012, which earned François Englert and Peter Higgs the Nobel Prize in Physics the following year. With its four primary detectors, ATLAS, CMS, ALICE, and LHCb, the LHC continues to produce cutting-edge results, probing the deepest structures of matter and testing the boundaries of the standard model of particle physics. Let's go through some mind-boggling finds. One of the more intriguing scientific developments at the LHC in recent years came from the LHCb experiment, which focuses on investigating the slight asymmetries between matter and antimatter by studying particles containing bottom quarks, or beauty quarks. In March 2021, the LHCb collaboration published a result that drew considerable attention from physicists around the world. The team had analyzed data from billions of proton-proton collisions and observed a possible discrepancy in the decay rates of B mesons, particles containing a bottom quark, into different types of leptons. Specifically, they measured how often B mesons decayed into electrons compared to muons, their heavier counterparts. According to the standard model, all leptons should interact in the same way with gauge bosons, aside from differences due to their masses. This principle is known as lepton universality. However, the LHCb data hinted that muons were being produced slightly less frequently than electrons in certain decay modes of B mesons. If confirmed, this would imply a violation of lepton universality. This is a clear sign of new physics beyond the standard model. This sparked widespread excitement in the scientific community. Various theoretical physicists proposed that the discrepancy could be explained by the existence of new particles, such as leptoquarks, which are hypothetical particles that could couple quarks and leptons, or additional Z bosons, which would be neutral carriers of a new force. However, it is important to recognize that the LHC regularly produces billions of events per second, generating petabytes of data each year. The job of physicists is to sift through these with rigor and skepticism, identifying patterns that persist under tighter scrutiny. The scientific anomalies observed at the LHC are the natural byproducts of humanity's effort to probe deeper into the fundamental workings of the universe. Whether these anomalies lead to the next big discovery or fade with further data, they underscore the dynamic, self-correcting nature of science. CERN's search for dark matter and hidden realms. At the heart of CERN's mission is the pursuit of the unknown, and among its most ambitious goals is the quest to identify dark matter, an invisible substance that does not emit, absorb, or reflect light, yet makes up approximately 27% of the universe's mass-energy content. Despite its abundance, dark matter has never been directly detected. Its presence is inferred from gravitational effects on visible matter, such as the rotation speeds of galaxies, gravitational lensing of light from distant objects, and the large-scale structure of the cosmos. To unravel the nature of dark matter, physicists at CERN are leveraging the unique capabilities of the Large Hadron Collider to probe beyond the established boundaries of the standard model of particle physics. The LHC, located beneath the French-Swiss border near Geneva, collides protons at energies of up to 13.6 TeV. These high-energy collisions recreate conditions similar to those just after the Big Bang, potentially giving rise to exotic particles, including those that could constitute dark matter. The LHC's general-purpose detectors, ATLAS and CMS, track and measure the energy and momentum of a vast array of particles produced in the collisions, including those that interact only weakly with ordinary matter. One key method used to search for dark matter at the LHC involves identifying so-called missing transverse energy. You see, in a proton-proton collision, the total energy before and after the collision remains balanced in the plane perpendicular to the beamline. If an event occurs where a substantial amount of energy appears to be missing in this plane, it could indicate the production of a weakly interacting particle that has escaped the detector without leaving a trace. This is an ideal candidate for dark matter. These events are statistically rare and must be carefully distinguished from background noise or measurement errors, which requires sophisticated data analysis and cross-checking with simulations based on known physics. Another promising avenue of investigation is the study of rare decay patterns of known particles. For instance, if a particle like the Higgs boson were to decay into invisible components more frequently than predicted by the standard model, it might suggest a hidden decay channel involving dark matter. In 2023, both the ATLAS and CMS collaborations reported updates on their searches for invisible Higgs decays, narrowing down the upper limit of such decays to about 11% of all Higgs events. These increasingly precise measurements are gradually constraining the possible properties of dark matter particles. Beyond dark matter, CERN researchers are also investigating the possibility of hidden sector particles. These sectors would be largely decoupled from the standard model but might interact with it through weak portals, such as heavy mediator particles. The phaser or forward search experiment, a new detector installed during the LHC's recent upgrade, began collecting data in 2022 with the specific goal of detecting light and weakly interacting particles that travel close to the beamline and would have gone unnoticed by ATLAS and CMS. Phaser is particularly sensitive to axion-like particles and dark photons. These hypothetical particles are predicted in various extensions of the standard model. Another experiment, SHIP or Search for Hidden Particles, is in the proposal phase and would be located at CERN's superproton synchrotron. SHIP aims to investigate long-lived particles predicted by hidden sector models, which could travel several meters before decaying into detectable particles. These investigations complement the LHC's high-energy searches by exploring regions of parameter space where new physics could emerge at lower energies but with long lifetimes and extremely weak couplings. All of these efforts are based on rigorous theoretical frameworks. One of the most extensively studied is supersymmetry or SUSY, which posits that each particle in the standard model has a heavier superpartner. Some of these superpartners, like the neutralino, are excellent dark matter candidates because they would be stable, electrically neutral, and weakly interacting. The concept of extra dimensions is another frontier explored at CERN. Theories like those proposed by Nima Akanihamd, Sovas Dimopoulos, and Gia Drali in 1998 suggest that additional spatial dimensions could exist beyond the familiar three. In these scenarios, gravity might propagate into extra dimensions, which could explain why it appears so weak compared to the other fundamental forces. While these areas of research may sound exotic, they are grounded in testable hypotheses and follow the rigorous methodology of the scientific process. They do not rely on mysticism, fantasy, or unverified speculation. Each proposed particle or interaction must be theoretically consistent, mathematically sound, and ultimately validated through reproducible experimental evidence. This is the foundation of modern particle physics. But not all claims associated with CERN are as grounded in reality. The portal conspiracies. Among the many internet-fueled myths surrounding high-energy physics, few have proven as persistent as the claim that CERN is trying to open portals to other universes. The idea gained traction around 2015 and 2016, coinciding with the Large Hadron Collider ramping up to its then record energy of 13 tera-electronvolts. Symbolic elements at CERN also added fuel to the fire. You see, there is a large statue of the Hindu deity Shiva, located just outside CERN's main building in Geneva. A gift from the Indian government in 2004 to symbolize the country's collaboration with CERN, the statue represents Shiva Nataraja, the cosmic dancer who, in Hindu tradition, symbolizes both the destruction and renewal of the universe. While the statue has deep cultural and philosophical meaning, it became the centerpiece of wild speculation. In online circles that lacked context, Shiva's depiction as a destroyer of worlds was miscast as a literal sign that CERN was dabbling in apocalyptic or metaphysical forces. Fueling the fire were legitimate but often sensationalized discussions in the media about CERN's theoretical explorations into concepts like extra dimensions and mini black holes. While extra dimensions and mini black holes are indeed a subject of study at CERN, the LHC does not, and cannot, create wormholes, portals, or gateways to parallel dimensions. Such feats would require energy densities and gravitational control orders of magnitude beyond anything achievable today or in the foreseeable future. To further refute the portal myth, CERN has made repeated efforts to communicate the LHC's safety and operational protocols. Before the collider's initial startup in 2008, and again before the 2015 energy ramp-up, CERN commissioned independent safety assessments. The most notable of these was the 2008 report by the LHC Safety Assessment Group or LSAG, which concluded that there is no basis for any conceivable threat from collider-produced phenomena. The report specifically addressed the speculative concerns about black holes and strangelets, concluding that if such exotic particles were ever produced, they would decay almost instantaneously and pose no danger.